is Magnus Carlson from Stockholm University. The title of his talk is Massey product in the étale cohomology of number fields.
So thank you so much for the organizer for inviting me to talk. It's a lovely conference. So today I'll be speaking about Massey products in the étale cohomology of number fields. So I think that the goal of this talk is to show you why this sort of niche thing is kind of interesting. Why you should care about Massey products in the étale cohomology of number fields. And by the way, I want to start with, please interrupt me when you don't understand something. So I should start also with saying that all the work I'm presenting here is based on joint work with Erik Ahlqvist. So Erik is sitting there. Hi, Erik. So this is part of a joint project that's been going on for some years, where we've been studying the étale cohomology of number rings. So let's start this talk by presenting this maybe strange two pictures. So here we had a Borromean rings, and here we have the 3 primes 13, 61, 937, and they're included into the set 0, 2, 3, 5, and all the primes from there. And then there may be somewhat strange claim is done that these are the same picture.
What is the first term? The set of primes?
0, and then I adjoin the primes. So this is really this underlying set of spec set.
Oh, I see.
Yeah. So I've been writing this in a bit of a strange manner. Emphasize that analogy is strange. So then you might ask, well, why are these the same picture? Because these look clearly not the same. How do we make sense of this analogy? So this is part of a philosophy in the arithmetic topology, which was studied by, amongst other, Morishita. And the analogy goes, as we've seen many times during this conference, that we should somehow view a 3-manifold M as being somewhat analogous to the spec of the ring of integers of a number field. Usually you say that it's a totally imaginary number field, and if it's not totally imaginary, you need to somehow compactify this, but I will ignore this point. And further into this somewhat weird analogy, we should expect that a knot K that's embedded in M should be somehow analogous to the inclusion of the residue field, spec of the residue field of a closed point into X. Okay, so now that's the analogy. Then the natural question is, well, what should then the integers correspond to in this analogy? Well, you need to compactify the integers, but if you do that, then spec said compactified, it should be sort of like the 3-sphere. Okay, so then we have first 3 lines here. But when we have knots, it's very natural to think about links. So we might ask, well, if we have 2 knots in S3, we can ask, are they linked or not? So what do they correspond to on this side then? And it turns out that I'm lying a tiny bit here, but not that much. If we should view in this side 2 knots, linked knots in S3, this would be kind of like 2 primes P and Q, such that P is not a square mod Q. So now we have the linked knots, and unlinked corresponds to that P is a square mod Q. So then we have what the Borromean links should correspond to in the number field setting. So this would be something like 3 primes P1, P2, P3, such that Pi is a square mod Pj for all I not equal to j. But somehow we're supposed to make sense to say that they collectively are linked. And then how do we do this? Because this correspondence between manifolds and number fields is a bit strange. How do we make sense of this? So there's one way to explain why you should view this as being sort of like the Borromean links. So let's study the Borromean links from a cohomological perspective, or like a homotopical perspective. So we have here 3 knots. Let C be equal to the knot complement of these 3 knots. What does it mean for them to be unlinked in the world of cohomology? Well, that's because if you see all of these knots will give cohomology classes and here, and they're unlinked since the cut product of those they're zero. This is like the zero linking numbers. So we see then that the knots are unlinked. But nonetheless, you can show using Massey products, which are some sort of like secondary cohomology operations, which I will not define with this lead now. But you can show that they are linked, that these three knots are linked because the Massey product of these three classes is non-zero. And if they were unlinked, the Massey product would be zero. So that's one way in why this is how you can show that these are linked collectively, but unlinked pairwise from the cohomology perspective. And this you can translate perfectly well into the world of étale cohomology. So now we have three knots, 13, 61, and 937. So recall that these are like correspond to knots under this analogy. What's the knot complement now? Well, we take away the 3 primes. Then you can show that the knots here, they're unlinked since the cup product with coefficient in F2 are 0. And you can also show then the Massey product that you get that's non-zero. But so these are collectively linked in somehow. And you see that this sort of like analogy uses the bridge of étale cohomology theory. That's usually how you go between the two worlds. You have like some 3 manifolds and number fields, and you go via some étale cohomology to see the analogy. Okay, so I think this is some sort of nice analogy. The question is, well, I think the obvious question is, why should you care? In some sense. So like, what can we do with this? I think that's a good question. What can we do with like these sort of analogies? How can we like apply them externally to things that are not purely in terms of number theory? So I'm trying, so as I said, my goal is to like try to show you why this Massey product in étale cohomology actually gives you something which is interesting externally from arithmetic topology. So more generally, I don't want to like argue that the étale cohomology ring, or like the multiplicative structure that's hidden inside the étale cohomology with spec of the ring of integers of number field, that this is an arithmetically interesting object. So let me mention some applications then of this multiplicative structure that's in the ring of integers of a number field. So let X is some open subscheme of the ring of integers of a number field K. So I'm going to write down some applications of when I say like this is like the cohomology ring of X with coefficient Fp, but also like related structures to this, like Massey products. So one application you can do is you can write down a presentation for the second quotient, like this, by the way, I should tell GK URP. So JKUR, that's a maximal unramified extension of K. And JKURP, that's maximal unramified pro P extension. This Galois extension of that. That's what it means, this notation means. People clear what the notation means? Okay, good. So what you can do with this ring first is that you can write down a presentation of this guy here, the Q2 of this group here. And Q2 is the second quotient in the lower central P series for P prime. So this gives you some understanding of some non-abelian group. I should say that these groups are very mysterious and it's hard to say anything concrete about them. What can you more do with these sort of like this structure? You can give some counterexamples to some conjectures on P-class field towers. You can give some examples of quadratic imaginary number fields, so that they have, with a property, they have class group of P rank 2, and such that these imaginary number fields has an infinite P class field tower. So if you don't understand all the terms here, it's fine. I'll explain them soon. So these things are not a priori related to Massey products. They're like proper number theoretic objects. And lastly, there are some applications to the Fontaine-Maser conjecture or the unramified Fontaine-Maser conjecture. And this is due to Questel-Mer. So these are 4 applications. So I will focus on these 3 applications, but I will mostly focus on these 2. This is interesting, but I'll not focus on it. So any questions so far? Yeah.
With the primes 13, 67, 900 something.
Yeah.
Is part of the theorem, I mean, like these are the smallest primes, triple of primes, or the unique triple of primes that you have this property?
No, there's definitely, and there's not a unique property.
Sure, okay.
But I mean, like if they're the smallest, I don't know, to be honest. Oh, sorry. Any further questions?
I don't think the smallest. I don't think I sent it to you. I have a large table now produced by a student.
Oh, wow. Okay. So let me continue then. So I'll explain a bit about how to connect Massey products to these sort of questions. And then I'll also mention a bit about this. So let me start with some background on what I mean by the class field tower. I'll explain then what I mean. So we'll fix a number field K, and then I will let HK as a Hilbert class field of K. So if you don't know what the Hilbert class field of K is, it's the maximal abelian unramified extension of K. So it's the commutator of the the commutator of the unramified group. It's the closed subgroup corresponding to that. Then there's this thing that follows from class field theory that's maybe a bit unsurprising. That's the Hilbert class field. The Hilbert class field is of infinite degree. And further, the degree is equal to the class number of K. So this is the Hilbert class field. We can, of course, iterate this construction. You can take the Hilbert class field of the Hilbert class field. You can take the Hilbert class field of the Hilbert, and go on like that. You take commutators of commutators of commutators of commutators. Well, then a very natural question is then, does the tower stabilize or not? And this is what is known as the class field tower problem. And you can further specialize this problem to something that's a bit more. It turns out that this is very hard in general to answer. This, I'm going to present a slightly easier version now. So if we fix a prime P, then you can speak about the P Hilbert class field problem. So that's the same question, but we replace HK by the maximal unramified, abelian unramified P extension of K. And then you continue with the tower like that. So that's what the Hilbert class field tower is, what you get by taking the maximal abelian unramified extension and iterating this. And the P Hilbert class field problem, you take just the maximal abelian unramified P extension. We continue. And turns out that this is a bit easier to answer. You see that this question here is equivalent to this question. So you're asking, is the Galois group of the maximal unramified P extension finite? Equivalent, because you see a P pro P group is nilpotent, and we're using the we're taking filtration. So some examples of this. So if we take K to be Q square root adjoint minus 391, this will have class group 7 Z mod 7 times Z2. And if I take the maximal and ramified 7 extension, I'll get something of class number 2. Then I can't continue. So the Hilbert class field stabilizes after one step. There's no unramified 7 extensions of HK because the class number encodes the unramified abelian extensions. But the length is not in general just 1. For example, you can have, if you take Q adjoint minus 445, then the 2 class field tower will have length 3. And you can have something of length 2 if you like take this. So, and it turns out that it's very hard in general to I think what's the maximum of the finite towers we know? Maybe that's like maybe 4 step or something like that. if it's maximum finite for step. So then there was like this conjecture back in the 1920, I think, by Artin and Furtwängler. And they conjectured, well, the P-class field tower always stabilizes. Well, but then Golod-Zafarevich showed that, well, no, the P-class field tower can be infinite. So I'll explain a bit how you can see now how Golod-Zafarevich did this, and I'll then also show you the connection to Massey products. So given pro P group G, you can consider what's known as a minimal pro P representation of the group G. So that's an exact sequence like this, where this is free pro P. And to say that this is minimal means that this is an image here is a minimal set of generators. And then you can further see that if let D, if the H1 with the coefficients H1G with coefficient FP, and if you let this R be equal to this H2 group, turns out that this D here, the dimension of this guy here, should be D equal to dimension. This is the same as the minimal number of generators of such a presentation. And R here is the cardinality of a minimal system of generators. So these H1 captures the minimal system of generators, and H2 captures the relations. So given such a pro P group G, you can consider the completed group ring, FPG. And then you can define a filtration on G, such that the nth filtration piece, it's those G and G, G minus 1 is in the nth power of the augmentation ideal, or the closure of that. This gives you a filtration on the group G. This is known as the Sassenhaus filtration. And then you can see, well, if you have the Sassenhaus filtration, you can, and you have a presentation of a group G, then you can see for each R that lives in big R here, you can consider what's known as the level of R. And that's the greatest integer K, that R lives in Fk, where Fk is the kth piece of the Sassenhaus filtration of the free pro P group G of F. So this is what you can do. I mean, you have to a pro P presentation, you can associate a level to certain relations. And here's the connection to the class field towers. So if we have like, we now pick a minimal system of generators, call them R1 to Rm. Then you can associate what's known as a Sassenhaus polynomial to such a presentation. So that's 1 minus dt, where d is the number of generators of F. And then you take the sum from I equal to 1 to, I guess it should be R here as well. I equals to 1 to R, T, Mi. Where here the mi's here, turns out that they're greater than or equal to 2. And the mi says exactly what the level of the relation Ri is with respect to Sassenhaus filtration. So we get such a polynomial where these guys here, the mi is what level Ri lies in the presentation, in the Sassenhaus filtration. Is this clear? Okay. Then what Golod-Zafarevich do, they show that if this polynomial, if it has a 0 in this open interval from 0 to 1, then G is infinite. That's the Golod-Zafarevich theorem, maybe upgraded by Koch-Penkov of some person, but that's the gist of what they do. From this, you can derive certain like conditions on involving D and R, which tells you when D must be infinite. So for example, if you see, like, you can compare this Sassenhaus polynomial with this polynomial here, 1 minus dt plus rt squared. Then we complete the square and we get this. Then you can see that if G is finite, we must have that the relations must be greater than d squared over 4. Because, well, plug in d over 2r, you puts out this, and then you see the inequality. You see that this gives you some relation between the number So how large the relation must be compared to the generators. This is like the classical Golgi-Farvich theorem. So, but let's not maybe note now that if the relations lie deep, it seems that it should be easier for this to have a zero. So we would like want to push the relations lie deep in the Sassenhaus filtration. But anyhow, you can then apply this inequality R greater than D squared over 4 to produce examples of K with an infinite P-class field tower. And this is what Golgi-Farvich did. Because you can show that H1 with GK URP with coefficient FP, this is the same as HOM from JK URP to FP. And by class field theory, this is precisely maps from the class group of K to FP. So then the dimension of this guy here is the dimension of the class group mod P. So D is the dimension of this. Then you can show also that if K is imaginary quadratic, the difference between R, which is H2 of this guy here, the difference between R and D is less than or equal to 1. So then you see if D is large, then this inequality, you will have R is less than or equal to D squared over 4. And by what we just said, this would imply that the Galois group is infinite. So for example, for P equal to 2, you can use genus theory to find K with large class group over 2. For example, you can do this. You join square root of these. So it would be nice. I mean, like now we have this problem with like this class field towers. I mean, it would be nice to like say, when is the given a number field K, when is the tower infinite? When is it finite? Maybe that's too hard. Maybe we should like start with like imaginary quadratic number fields. See if we can like decide when is an imaginary quadratic field, when is the P Hilbert class field finite or infinite. Let's see if we can say something about this. That's the question. So let's say we even restrict to odd, because maybe that's P is weird, 2 can be weird. It turns out that, well, you can use it's easy group theory. The class field P class field tower is finite if D is equal to 1. It's the Burnside basis theorem, more or less. And by an enhanced version of Golgi-Farvich, will be infinite as D is greater than 3. I will explain why in a moment. But it turns out we were completely in the dark when D is equal to 2. There's like no known, we have no expectation what to happen in general. I mean, up to very recently, we had like no examples of an infinite tower. So no, this is very dark. Turns out then, however, that you can use cup products and cohomology operations to help to determine when P class field towers is infinite, when they're infinite. And you can use this to give like the first examples of infinite P class field towers for D equal to 2 for imaginary quadratic number fields. Let's see. So any questions? Everything's clear?
What kind of cohomology operations do you think of? Massey product?
Massey products. I'm thinking of. I mean, like 3-fold, 4-fold, and so on.
I have a quote from Koch.
Oh, right. Yeah, what? Yeah.
Because there was a colleague of Janssen and Wingberg who had a connection. So Koch said about H2, well, it's relations, and Massey products have to do with the relations, and they are too complicated to be useful. You can the name there.
Yeah.
Earlier you mentioned that if the relations have high level, then it's more likely to have a zero.
Yeah.
Is that the technical?
I mean, I'm going to go into it. We see an example. Why? Right. So that's good. I'm going to follow up on that. I just asked. So, if I have a pro P group and a minimal presentation, I'll now let the generators be called Fi, and I'll say that R is of H2. This R be of rank R is like a normal subgroup. Here's some facts I want to present to you. So here's the first fact. So given a minimal set of generators, Vi of R, so here, then you can write Vi equal to the product from k equal to 1 to d of f k p times mk for mk, some exponent, and then the product over all a less than b of this commutator fa comma fb, then some exponent here as well, and then v prime I, where v prime I is in level 3 with respect to the Sassenhaus filtration. It turns out what governs these exponents will be cup products. So you see that the exponents here that appear in this presentation, like this way of writing the relations, they're governed by the cup product from H1G to H2G. These are like the two facts. And what you can in particular show that if the cup product is 0 here, then the relations will lie in level 3. So you can see that the cup products will somehow, if we can understand this, we can say something about what the MK are and thus understand the relations better. And better if they're 0, the relations lie in level 3. And whether they lie in level 4 will be controlled by threefold Massey products. And that's certain secondary cohomology operations. Okay. So here's a small aside related to this. So well, you might ask, well, can we like compute the? I mean, like if you give me a number field, can I like compute something related to like compute this integers? And you can. Here's a small aside. So if K is a number field in P prime, and you let S be a finite set of places, then Eric and I, we have a computer program, and we have a formula that gives you the cup product here, but it goes for the étale cohomology of the spec OKS. And then by using this, you can get an effective way of writing down a presentation for this JKS mod, the third part of the Sassenhaus filtration. And we have a computer program, which Eric has written very nicely, which takes as input a number field K and a prime P, and precisely spits out this guy, this quotient. And this turns out to also be the second step of the lower central P series of JQRP. Like you can do this for some number fields. Here we have some cup product matrix that you can associate to K. In this case, then defines splitting field for this polynomial. If you then do the calculation for the cup product matrix, you can see that this quotient will be a group of order 2 to the power of 9, and this will be the interesting relations occurring in the group. But this is something you small side. So now let's specialize the case where K is quadratic imaginary, quadratic imaginary is odd, and D is equal to this K mod. Then the cup product from H1 JQR with coefficient FP to H2, that's 0. It's always 0 for P odd, because if you see Z mod 2 will act on the cohomology group. This will split into eigenspaces, a plus and a minus eigenspace. And then it turns out that, well, the plus eigenspace in both degrees 1 and 2 is 0. So then you see that means that the H1 will only have a minus eigenspace. So then take X and Y in the minus eigenspace, and I cup them together. Then this will land in the plus eigenspace, but that's 0. So this means that the cup product is always 0. Of course, you need to show why is the plus eigenspace 0 in general, but it is not. So we just learned that for P odd and quadratic imaginary, the cup product vanishes. But this means then, well, the relations of a manifold presentation, they will lie in degree at least 3. That's good. So that means that the Sassenhaus polynomial will be 1 minus 2t plus tm1 plus tm2, where the mi are greater than or equal to 3. But you see, if all the Massey products vanish, then you can use some further eigenspace argument to show that also the fourfold, if all the threefold Massey products vanish, you can show that all the fourfold Massey products vanish as well. That means that the MI will be greater than or equal to 5. But then you can see that if you have such a polynomial, this will have a 0 on the interval from 0 to 1. So the p-class field tower is then infinite. So this is the way you can show that if the Massey products, threefold Massey products vanish here, then the Sassenhaus polynomial will have a 0 in the. I should say, like the discovery of this is not new. This is due to, I think, at least Cameron McLean. Yes. So this connection with the Sassenhaus polynomial and Massey products is not due to Eric and I. But if threefold Massey products vanish, then the p-class field tower is infinite. Then there was this McLean, I don't know if I pronounced his name correctly. So he did some analysis of the possible Sassenhaus polynomials you can get for quadratic imaginary number fields in p odd. And then he made the following conjecture, which if true would be absolutely fantastic, which is the following conjecture. So suppose that k is quadratic imaginary, let p be odd, and suppose also for simplicity that it's greater than 3. And suppose further that the class group of k mod p has dimension 2. And you then let x and y be a basis of H1 JQR FP. Then it turns out that the p class field tower is infinite. Then he conjectured that the p class field tower is infinite if and only if these two elements, the Massey product of xy and the Massey product of yx, if these two elements in H2, if they are linearly dependent, then the tower is infinite. So linearly dependent if and only if infinite. That's a conjecture. And clearly if this was true, I mean, it would be a fantastic statement because we would put some order into like the p rank equal to 2 situation for quadratic imaginary number fields. So when I first saw this, I tried to prove it. I tried hard, but I got nowhere. And it's for good reasons because the theorem is false, the conjecture is false. So this is due to Eric and I. So the conjecture is false then, because you can see the field at k adjoins square root of minus 90861 for the prime p equals to 5. This is a counterexample to the conjecture. We can show that these Massey products, they are linearly dependent, but the p-class field tower is finite. And then Eric and I further, you see, there was also like this connection between like when showing when p-class field tower is infinite or not. And we also show that the following, which gives some understanding of infinite towers for quadratic imaginary fields. The theorem is that suppose that k is imaginary quadratic and the class group is p rank 2. Choose elements x and y, which correspond in the H1 JQR FP. And suppose that they're a basis of this guy here. See, these x and y, they correspond to unramified p extensions Lx and Ly of k. And you can show that for p greater than 3, the Massey products xxy and yyx, they vanish if and only if these both Lx and Ly have class group of p rank at least 4. So somehow the vanishing of these Massey products are encoded in the the rank of certain unramified p extensions of k. And then in particular then that show that if you have can find a quadratic imaginary number field with Lx and Ly, so they have class group of p rank at least 4, then the tower is infinite.
The question in this false conjecture.
Yeah.
You choose generators x and y and you form these Massey products, and they are non-linear kind of. So why would it be enough to choose only generators?
But you have like this juggling formulas then for these situations. Then you can see like if they're so I mean then you can like show that what we're doing basically is that so then you can, they're not linear, but juggling formulas would allows you, gives you a lot of room then to say like play with them. But I mean they're not linear in general, right? But You can,
So if they vanish for generators X and Y, they will vanish for all pairs?
yes. And further, we like actually give a very, very terrible formula for Massey products. It's not something you can do by hand, but you can do it by computer. So that's this informal theorem then, that if you have K is totally imaginary, and you have X, Y, and Z, so the cup, X cup Y is equal to Y cup Z is equal to 0. Then under some certain mild technical assumptions, there is an quote, effectively computable formula for the Massey product. But by effectively, you can put it into a computer, but it is not something you would ever be able to compute by hand in general.
That formula involves explicitly solving a lot of norm equations.
Yes. Yes. And then as a corollary of that, we give like the first examples of imaginary quadratic number fields with class group of P rank 2 and infinite towers then. So you can see that these, if I take the prime P and the discriminant D, then all these pairs give examples of fields with an infinite P class field tower. Repeats this. This is the list of examples. So any questions before I move on?
Maybe we could mention that in the counterexample to the conjecture, we like the finiteness result is
It is not due to, I mean, we're like the finiteness result here is due to Daniel Meyer. Yeah. Using some P group, very like computational proof.
Yeah, one comment about that.
Yeah.
It would be interesting if you had some very large prime.
Yeah, right. I think we're like done with like,
Very large.
have we tried 7? Or did we try 7? Did that work?
yeah, but it's like so for 3, we like the list is almost complete.
Yeah.
For the prime 5, it gets like, because we have this time limit, like if the program runs for more than 5 minutes, we move on to the next example. But like the list gets more and more like
So we have like compiled some database and like some Massey product statistics also. For quadratic number.
Maybe I missed this. You said for 3, the list is almost complete. Is this a finite? Like it's finite?
No, I mean like what Eric says is we have like complete list. You can
so we compute like a list from this database, this what is it called, LMF. And then we computed this for like 10,000 fields or something. But like sometimes these implemented algorithms in Paris, right? So the program is written in C using this old library called Paris. And for some examples, it just took forever. So then I had like a time limit, like move on to the next example after like 5 minutes.
Okay.
And the higher the degree is, the longer it takes. So it's harder for bigger primes.
So we have quite a complete list for people to 3 and all the quadratic imaginary. Yeah.
And I mean the list can be much more complete now, that because I mean the way we did it was that we actually computed Massey products. But then when we looked at the list, we saw that all the examples where it's infinite seems to satisfy this thing that the P rank of the extensions is at least 4.
Yeah.
I mean, if you write a program like that instead, it's
much
much
faster,
faster.
yeah.
Then you can get a much more complete list.
So let me maybe see how much I can do in 10 minutes with like the sketch of how the argument goes. So what we do is then we like disprove McLeland's conjecture and prove the characterization by Vanish of managed products by giving a formula for Massey products in the Galois cohomology. So the strategy for this, let's choose that. First, that we relate Massey products to certain connecting homomorphisms. This is a very important step. And then you compare the Galois cohomology to the étale cohomology of your spec OK. That's broad strokes the strategy. Then, to show that McLeland's conjecture fails, you construct a K with a finite class field tower. This is due to Daniel Meyer. This finite class field tower we construct, but where these are linearly dependent is what I should say, where these are linearly dependent, these two clauses. Do not vanish. And then class group characterization of the vanishing. I mean, we said that these Massey products vanish if and only if the P rank of certain P extensions were large. To prove this, one use a connecting homomorphism to relate the vanishing to the P ranks of unramified P extensions. Let me maybe say some words about how to relate Massey products to connecting homomorphisms. Some details. So here's a new way, I guess, to sort of a new strange way to construct Massey products. So let G be profinite and P a prime. So given a cohomology class Y in the first cohomology of G, you can construct a short exact sequence which goes FP, VY, and FP. Here VI is as a vector space would be FP squared, sorry, FP squared. VI is FP squared. And the G action is given by this matrix. So there is such an exact sequence, and this uses this cohomology class here. This would be FP squared. So the two-dimensional vector space FP. Then you can show this is what is known as, I think, the Arason exact sequence. Then you can show that the connecting homomorphism, it is the cup product of Y. Okay, so we can realize the cup product in terms of connecting homomorphisms. That's not surprising at all. So suppose now that we have further classes X and Z in H1. And suppose that you have that X cup Y is equal to 0 and Y cup Z is equal to 0. This is required for the Massey product to be defined. Then you see there will be elements WX and WZ in H1G VY, the maps to X and Z. This is because you see the connecting homomorphism is precisely coupled with Y. It means that these lie in the kernel of the connecting homomorphism. So by exactness of the long exact sequence, there are WX and WZ that maps to X and Z. Is this clear? Okay. Then you can form this element, which is WX cup Z minus X cup WZ. And this lives in H2 G with coefficient VY. You see then what happens if I take this class and I map it into here? Well, Vx cup Z minus X cup WZ, it goes then under this map to X cup Z minus X cup Z, which is 0. So this means by exactness, so there's an element alpha in H2 GFP, which maps to this guy. And then you can define quotation mark Massey to be all the elements you get by varying WX and WZ, and all the elements here maps into this such a map guy class here. It turns out that this is almost the Massey products, but it's very much easier to calculate in general, and in many cases coincided with the regular one. So this is a strategy for computing Massey products.
You mean by almost?
I mean that you see that this has a larger indeterminacy. So that's why it's not, the indeterminacy is larger for this. So we need the indeterminacy to be equal. So that's the connecting homomorphism step. And then there's the step with Massey with étale cohomology, which we use them to get the formulas. So if X is equal to spec OK, you see there's a canonical map of sites between the étale site of X and the finite étale site of X. And this is equal to the classifying site of pi1 of X. And this is BGKUR. And this induces an isomorphism on the first cohomology.
Could I step up just a second? The previous thing almost fit.
Yeah.
For P equals 2, is it still almost?
Yeah. Yeah. So you have such a classifying map, which induces isomorphism in H1. Then the philosophy is then that the cohomology of this JQR, this mysterious, but this étale cohomology of X, that's much, we like to be here. It's geometric, we can do things here. Here, we're scared, we don't know much. So we want to be here. So that's why we're using F to go to X. And there we can like do calculations and compare the cohomology of X with cohomology of JQR. And it turns out that you can calculate the Massey product X, Y, and Z in H2XFP. That's how we get the formulas. And why is X so nice? Well, one thing is geometric, but also it satisfies this Artin-Virdrier duality, which is some arithmetic Poincare duality. So it says that if you have a locally constant constructible sheaf F on X, you have this perfect pairing going from X3, Y minus YX, and then F with coefficient in GM, where GM is a sheaf of multiplicative group. And take times HIX with coefficient in F. You can cut these together, get something in H3X GMX. This is then isomorphic to Q mod Z. They have a perfect duality between these groups. And what can I, yeah?
So you assume it's totally imaginary.
Well, but I mean, like we have like we have some papers where like you do it for even, I mean, you have like complexly supported cohomology in general, or like complexly supported flat cohomology, which works fine as well. If you have like, I mean, like if there's like this,
You can rectify. You
There's
can
like this-
include the real primes into the definition of the outside.
there's like two ways to solve this. Like Sink has a theory, and Bienenfeld has a theory. And Eric and I have two different papers. In one paper we use the Bienenfeld's version, another paper we use the Sink's version. So I see you can make sense of this. But for real places, it turns out, do you want to just look at the unramified and infinite places, or do you want to allow ramification in infinite places? But you can make sense of it in both cases. But we're now assuming the total imaginary number field for technical reasons. And what we do then is that we're going to take resolutions of the sheaves FP and VI and FP and VX, tensor VY and VX. And these are sheaves of, these are JKUR modules. So I can then correspond to locally constant sheaves on X. So I can take resolutions of these. And then by using this one gets, and using Artin-Virdrier duality, you get a concrete formula for the Massey product. So I have some more, but I don't really have the time for that. But I just want to show you that what you do when you take the resolutions, you get things like this.
Can you show the preceding slide?
Yeah.
Yes.
Yeah. So we're like, what we're going to do, we're taking first the resolutions of these guys, VX tensor VY, and then we take a resolution of GM. So when we take the resolutions of, when we take all the resolution, we'll get this diagram, which looks horrible.
What was delta on the previous slide again?
Delta.
Oh, okay,
It's
it's,
connecting homomorphism. Yeah. And you see, then when we take resolution of the locally constant sheaves, by comparing them to certain group, I mean, G modules, where this is maximum ramified extension, you get a diagram which looks as follows. And these are certain maps, which so you get this diagram. And then in the end, to make calculations, you have to work with this matrix. So this is as horrible as it looks. This is the norm of the certain like extension K. This is the divisor, and this is like the sigma y minus 1 with sigma is the Galois generator, and this gamma, where do you have the gamma? Also some Kolviagin derivative that appears. So it's a terrible formula. And what you need to do is that you map some guy in here, and then you must like see, so this turns out to be quasi-isomorphism. So you must invert this arrow. So then you must like reduce this by this chain complex to get that it's an image of this. And then when you pull back here, then that's the sort of like the element you get. It's a messy computation. Actually, this computation uses a whole lot of class field theory to make it work. I mean, like to see that you can do such a thing. And then this
Formula is nice when you have X, Y.
when X and Y are when X is equal to Y, then the formula is nice. But for X and Y and Z, it's hopeless, more or less. There's like the connection to class field, class groups, which I don't think I have the time to go into, but yeah. So thanks so much to the organizers. And also thanks for your listening. Very nice.